So in this lecture, we are going to look at performing routing in wireless networks. So what is routing and what is the goal? So if you're given a source and a destination device, how would you create a connection between the source and the destination device to be able to send packet between the two? And some of the simple techniques involve, for example, broadcasting or creating tree-like structures. However, more complex techniques may also be used to send packet from the source to the destination nodes, especially in IoT devices where many of these devices could form a mesh and they could then forward the packets over multiple hop for the packet to be transmitted between a source to a destination node. So let's first start by putting it context to a wired network. In case of wired networks, routing is trivial if all the nodes are connected to each other through wire. You can just send the packet to an appropriate interface. However, this becomes, of course, much more challenging if there are n nodes because you would need n square links. So it really grows very fast. So what is the solution to this complexity? We actually use this solution in our day-to-day life because many times you would have your computer or a router connected to a wired network, and typically they're connecting to a big switch so we can reduce the number of links by having a large switch with n links, and by adding even more hierarchical switches that are connected to each other, we could reduce the number of links required while being able to connect the device to a large number of other such devices. However, of course, as we add more routers and switches, the routing gets more complex to perform from the source to the destination node. However, conducting routing or taking packets from one wireless node to another in a wireless network is much more challenging. When wireless network a single hop, like for example, arranged in a star topology, a good example is Wi-Fi networks, it can be trivial because you just send a packet from the node to the base station. However, when the packets need to travel over multiple hops to reach the destination device, it becomes extremely challenging. And then we have to ask questions such as, is it better to go through multiple hops or a single hop? How do you find and select the best path? And especially if you have multiple paths from the source to the destination node, which path do you take? So let's start with the question. For traveling the same distance, is it better to have a direct path between node A and B, or should we have a packet go through multiple hops as we have in the second case between the node A and B? From the complexity wise and keeping the network simple, a single hop would be considered to be better. You just send a packet to the destination node. However, from the energy consumption point of view, is it still the best solution? If we recall the free space path loss model, the receive power is a function of the transmit power and is inversely proportional to the distance. And this distance is raised to a power of some exponent which actually looks at the path loss in different environments. Now, if we transmit over one link, the transmit power required is P1. On the other hand, if we transmit over n hops, the transmit power required at each hop is going to be much lower. However, a question for you to think about is if the transmit power in an aggregate over the network would be still lower, because if let's say at each hop you're requiring a lower transmit power by actually transmitting over multiple hop links, but on an aggregate, if you take all the nodes in the network, is the transmit power lower than a single hop? And this is a question that I would ask you to sort of like think about and then sort of like reason what would be the right solution. So now let's look at some of the simple routing solutions that exist. So first we can have broadcast. A node sends a message to everyone who can hear it. Next, we can have sort of like a star topology. There is only one location to send, which is the parent device, and the parent stores all that information regarding its channel. Finally, we also have tree topology where we have two choices: send it to the descendant or a parent, and each parent needs to store information about the child. So one particular topology that is very relevant to IoT devices and network is one where many nodes send the data to a gateway device or a cellular base station or other such more powerful devices. And typically in IoT device network, all devices except the IoT or sensor device would be as simple as possible. And each device only remembers the next hop to the gateway. And this is also sometimes called many-to-one routing, as we demonstrate in this slide. So now let's talk about communication using wireless mesh, which is highly relevant for us in the IoT network. It is typically formed by network of static wireless nodes. These devices forward packet to each other such that ultimately it is routed from source device to the destination node. And the key challenge is regarding interference and self-interference of packet, as these are transmitted over multiple hop links. Hence, the routing protocols often try to select route that minimizes these negative issues so that the packet could be delivered from the source to the destination node with the highest reliability. However, mesh topology makes the routing question to be complicated. We can have multiple hops in a route, and there can be multiple routes between the source and the destination node. As an example, in the given topology, we can have several paths that take us from the node A towards the node F. It can be A, B, C, F. It can be A, D, F. It can be A, D, E, F. And it is typically a graph theory question if you sort of like want to look at it from that perspective, to select the best path that minimizes some metric. So now let's look at how these routing protocols can be classified. We can broadly classify these routing protocols as a proactive or reactive. What it means, let's look at it in detail. So how does a reactive routing protocol works? They build a map of all the routes in the network, and these paths are then developed to react. They build map of all routes in the network, and how it works is that basically when there is a arrival of packet, it sort of like results in the discovery of paths, and then these paths are then cached at the router or the edge or the device that is sort of like taking part in the routing decision. So in reactive routing protocols, it's the packet being transmitted actually initiates the process to discover the packets, discover the routes in the network. So reactive routing protocol are also called on-demand routing protocols. They establish routes in response to the need for data transmission. And the individual nodes don't maintain a complete map of all the routes in the network. So one particular node does not know about every node that exists in the network. They discover these routes when they are required and then cache these information for future use. So here's a sort of like a small timeline on how these routing protocols would work. The first stage would be route discovery. When a source node needs to send a data to a destination node and it does not have a valid route, it initiates the route discovery process. And the source node typically broadcasts a message called a route request, which is RREQ, to its neighboring nodes. Then we have the route propagation, where the neighboring node receiving the RREQ message checks the routing table or caches for a route to the destination. If a valid route is found, a route reply message is sent back to the source node. And if not, the RREQ message is then propagated to other neighboring node, and this process continues on that allows other nodes in the network to keep discovering the paths. Then once the third phase is route establishment, and once the RREF message reaches the source node, the route is established and the data transmission from the source to the destination node can begin. And the established route is then cached for future use. That means it's stored for future use. It typically has a defined expiration time to ensure that the information doesn't become stale. And finally, of course, once we have maintained the route, we need to also maintain the routes. And this is very important for battery operated wireless devices, because they can actually run out of battery, and maybe some of the routes that you have discovered might not continue to be good. So as long as the route remains active, the source and destination node then periodically exchange messages to maintain this route. And if a link within route breaks, then a route error or RERR message is sent to the source nodes, which then initiates this process again. So we talked about that the RREQ is one of the messages that is sent for discovery, and typically it has a hop count, and it starts at 1 and it's incremented by the transmitter along each hop that it sort of like traverses. And we are going to look into it in detail with the one example. So one example is that AODV protocol, and let's say we have a node A which wants to send packet to node F, and it wants to discover a path and then sort of like set data transmission between the nodes. So what would happen is that in the first stage, A wants to find a route to F, so it sends an RREQ message. So B and D receive this message and use this to add a routing table for A, and then they propagate this message. And you should note that the hop count has increased to 2. So A and D ignore the duplicate request, and then C basically uses this message that has been sent by B to add a table and then propagate this message again. And now in the case, D propagates a message and it allows E to discover the route, and then this process continues. Then C forwards the packet. So what happens is now that the RREQ message has sort of like distributed across the node, and then finally the node F has received this message that, okay, A wants to discover a path, and sort of like all the nodes have sort of like exchanged RREQ message. So now what happens is that the node F sends a message called, which is root response, which is a unicast to on the newly constructed path to say that, okay, the route has been established and you can now start sending the data over this route. So here we have the example that the node F has now sent RREP through one of the path that has been established. So it sends this message through FDA, and then A would use this newly established path to send data to the node F. So this is a reactive protocol. So as you have seen that the sort of like the step of A to discover, to send message to F allows the network to discover various paths. And once the paths has been discovered, it uses these paths to send a data transmission from node F, A to F. So of course, we talked about that some of the nodes or the links could be disturbed especially in a wireless communication. So typically for IoT devices like running out of batteries. So you can also send RRER message, which can be used to sort of like discover paths again. So what is the trade-offs in the reactive routing? So there is an upside that there is no transmission unless there is a demand. So you are not sort of like sending all these messages in the network and sort of like using the energy on your device unless you really want to send message from particular node. So during the time when there is no data transmission, it's very efficient. The downside is that you need to send all these messages before data can be transmitted. So you are spending this additional energy to discover routes and sort of like update paths, which can be sort of like something that can drain out your energy on your node. And so it has an upside, but for certain applications it might make sense. For certain applications it might not be the most optimal choice. So what's an alternative to reactive routing? An alternative to reactive routing is something called proactive routing, where routes within the network are pre-established and maintained. So devices in the network periodically exchange routing information to keep the paths updated, and they save these essential routes and adapt them when the network topology changes. And so the advantages of proactive routing is the routes are readily available when needed, and it reduces the latency because you don't have to exchange these messages that we talked about for you to discover. So the nodes know the routes that are there in the network, and they just use this path for data transmission. However, the downside is that it requires increased memory and processing overhead on the router device because it has to keep record of all these different routes that exist in the network and also maintain this path. So one example of a proactive routing protocol is something called distance vector algorithm. It maintains a routing table at each device, and it contains the shortest distance to every other node in the network and the next hop to reach them. So by periodically exchanging routing information with the neighbor, the algorithm ensures that these paths are updated in the table for the data transmission is required. So when constructing routing parts, finding the optimal path involves selecting an appropriate cost metric to evaluate the route from the source to destination. And the optimal path may or not always be the one that is the shortest number of hop from the source to destination node. So when you're constructing this routing path, even in the case of example that we have on the slide, we have multiple paths that can take you from node A to node F. So you are going to use some cost metric, and this cost metric might give you path. For example, a path A to D and D to E and E to F might be more optimal if you consider one particular routing metric compared to just taking the shortest path, which might be A, D, F. So one of the commonly used routing metric is something called ETX, which is expected transmission count, and it aims to minimize the number of expected transmissions. And this measures the link quality over time, and it assesses its reliability by considering factors such as packet loss rate. So we'll look at ETX in greater detail in the following slide. But we can also have other metrics that can be used for constructing routing paths. For example, we could have routing sort of like metric used with the routing algorithm that actually allows you to have better spatial reuse, so that you could, for example, have communication such that node A, B, and E, F are communicating at the same time, and they are not sort of colliding. You could also have routing algorithm that would want to conserve energy, that prolongs battery life on devices, so they can prioritize routes that minimizes the energy consumption, or sort of like balances it and prevents a depletion. Or you could also have some custom metrics or complex combinations. So you could have some combination of these routing metrics that could be employed to sort of like ensure routes that meet specific requirements of the network. And these could be, for example, considering latency, bandwidth, reliability, or security. So the goal is that by choosing this appropriate cost metric, or cost metric, or a combination of cost metric, routing algorithms can figure out routing paths that are very sort of like unique, or for a particular network and application. And it then leads to better usage of the resource, which is the spectrum and also the battery on the IoT device typically. So now let's look at one routing metric that is very commonly used on wireless networks, and it is called expected transmission count. And as the name suggests, it is a routing that estimates the number of transmissions required for successful end-to-end delivery of a packet, and it takes into account the packet reception rate along each link in the path. So let's try to understand this with this an example. So let's consider the path A to B, B to C. And now if we look at the link A to B, let's assume that the packet reception rate is 0.8, which means that 80% of the packets are successfully received. So the ETX of the link would be an inverse ratio of this, which will be 1 over 0.8, which will be 1.25. Now, if you look at the link B to C, if the packet reception rate for this link is 0.5, the ETX would be 2. Now, what would be the ETX of the overall path? So the ETX of the overall path can be actually looked at the summation of the individual link, and in this case, it will be 3.25. So the overall path ETX of 3.25 represents the expected number of transmissions that would be required for successful end-to-end delivery of a packet from A to C. So a typical routing algorithm would want to utilize the ETX metric to minimize this value, which is the overall ETX in the path, to be the lowest, because by selecting such a path, you can ensure the high packet reception rate, less retransmissions, and a very reliable and efficient communication. So one thing we are going to talk about is that many routing protocols focus on finding the shortest path between two nodes, where the shortest path doesn't mean the shortest hop, but it's sort of like defined by a parameter length. And this length could be one of the metrics that we have discussed, including ETX. So one of the popular shortest path routing algorithm is something called the Dijkstra algorithm and Bellman-Ford algorithm. And many of these algorithms, by minimizing a chosen metric such as hop count, ETX, latency, energy consumption, or a combination of them, they can identify the shortest path between a source and destination, and that allows you to route the packets or messages in the most efficient manner. So now let's talk about routing for IoT devices. So typically IoT devices are arranged in the form of a mesh. And the important difference from IoT device compared to other wireless devices is that you want to design mechanisms that are highly energy efficient, and the IoT devices are duty cycling. And this makes the design of these protocols to be challenging. So one of the challenges with the sort of like designing routing protocols for wireless devices such as IoT devices is that each node needs to sort of like figure out how good the link is to the nodes in the vicinity. You need to discover who are the nodes in the vicinity and how good is the link. So how do you do that? You do this task by actually performing some kind of measurement. What you do is that your node sends some beacon messages to other nodes in the network and uses these beacon messages to figure out how good the link is. So what are the parameters that you could actually discover? You could, for example, use things like packet reception rate. So you could be sending, let's say 100 beacons to one of the neighboring node and figure out how many packets have been successfully received. And you repeat the process over a period of time. It can give you some estimate for how good the link is. Or you could also sort of like, if you are maximizing the best link in terms of the signal quality, use something like receive signal strength indicator. So you could sort of like send these beacon messages and the receiving node could figure out, okay, how the signal strength look like, and use this as a metric to sort of like figure out the link quality of all its neighbors, which can then be used for building a routing tree and sort of like performing routing in an efficient manner. So one thing you should consider is that many of these links, especially when you talk about low power wireless, could be asymmetric, which means that a link, which means if you are sort of like transmitting between a node A to B, uh, the link between A to B might be good, but B to A might not be as good as the link in the forward direction. So typically you could have that the receive link is not as good as in the forward direction. So it's not necessary that the links would be in a symmetric manner to be very good. So finally, let's just briefly introduce flooding. So flooding is sort of like mesh equivalent of broadcast. What is broadcast? That you send message to all the nodes that are connected in, let's say, the wired network. So in flooding, you want to actually have a message propagate to all the nodes that are available in the network. So each node sends to other node, and eventually basically an information can traverse through all the nodes that are part of the mesh. So let's say you have many nodes over multiple hop, and you want to send the information, let's say that there is a fire, then these nodes will quickly do the flooding and send this message to all other nodes so that the information can propagate in the shortest time over the wireless network. So how the question would be, how do we make the flooding process stop? You can have things like TTL or something like a counter that actually decreases at each sort of like hop. And when the counter reaches 0, the node could drop that packet. So there are different ways of allowing the flooding process to stop. So with this, we come to an end of this particular lecture. Thank you very much.